Now, before we state and prove our first theorem in this chapter, I want to make a note from the previous talk. Based upon the definition of what it means for a function to be continuous, if you have a function that has a whole bunch of, I'll call them singleton points, that's the entire function. By the definition, this is a continuous function. And you can verify that by going through the definition yourself. Basically, it says, why is it continuous at, say, this point? Let's say that's the number 1. Well, for every epsilon, doesn't matter how small I make the epsilon tube around that, I can make delta so small that that's the only point in there. By the definition, it's continuous at that point. That is absolutely the uninteresting cases. And if I have a function that is continuous and smooth for in some interval, and then I've got some straggler points outside, I'll pretty much ignore those. I'll say we know it's continuous at those points. Let's discuss where it's defined on this interval. And I guess a nicer way of saying that is, that's the easy case, kind of the default case. We're going to look for accumulation points. And that's where we're going to, where the interesting cases are to prove continuity of a function. All right, well, the first theorem we have is theorem 3.1 that says this: if f is a function from domain capital D into R, and x0 is an element of the domain, and x0, where x0 is an accumulation point of D, then what that means, the following statements are equivalent. These are really important theorems. For example, if you need one day to prove that a function f is continuous at x0, you can prove either this is true or this is true and you're done. It might be easier. One of them might be easier. Okay, so f is continuous at x0. That's equivalent to saying that f has a limit at x0, and that limit, as x goes to x0 of f of x, is the value f of x0. And then the third one, going back to sequences, says that for every sequence xn in D, in the domain, every sequence of numbers that converges to x0, the sequence f of xn is going to converge to f of x0. Now, in order to prove that these three are equivalent, I'm not going to have much room to write down here, but let me tell you what we're going to do. Hopefully you remember that, and I know what order we're going to do. I'm going to show that, well, let's say, one way of doing it is this. In order to show that they're equivalent, this double arrow, this if and only if, the biconditional means that they're equivalent. Well, one way of doing it, the long way of doing it, is showing that 1 is equivalent to 2, which is equivalent to 3, and 3 and 1 are equivalent as well. Now, by transitivity, we could remove one of these. By transitivity, if 1 is equivalent to 2, and you know I'm not meaning the numbers 1 and 2, the statement here, statement 1 is equivalent to statement 2, statement 2 is equivalent to statement 3, and statement 1 is equivalent to statement 3. We would get that for free. But even now, this means we would have to do 4 proofs. If we went both directions, 1 implies 2, 2 implies 1. Then we would have to do here for this biconditional, we would have to do 2 implies 3, and 3 implies 2. Do you remember how we could do this with maybe one smaller step, one fewer steps? Anybody remember? We don't have to do the biconditional part of it. We can simply do this. And this is what I'm going to do. 3 implies 2. 2 implies 1. And 1 implies 3. So we're actually getting the biconditional. We're getting it both directions. The way we know that 1 and 3 are equivalent, we know that 1 implies 3, and 3 implies 2, which implies 1. And by transitivity, that means 3 implies 1. And this is what we're going to do for this proof. So I'm going to do, I think I could probably squeeze the first 2 in here. Proof. We will show that the third statement implies the second statement, which implies the first statement, which implies the third statement. I could have drawn my arrow all the way back here. We basically have three cases to prove. 3 implies 2, 2 implies 1, and 1 implies 3. I know I have enough room for the first part. The first case is 3 implies 2. So, every sequence xn in D that converges to x naught means that the sequence f of xn converges to f of x naught. Well, that comes straight from theorem 2.1. By theorem 2.1, when that holds, we know that the limit as x goes to x naught of f of x is f of x naught. You can go back, I'm not going to write that theorem down, but it's the one that obviously discusses sequences converging to x naught. If all of them have the f of the sequences converging to f of x naught, that means this is true. Sorry, it means that this is true. 3 implies 2. So that's the whole statement of the first proof. 2 implying 1, I'll need a little bit of space, not too much. 2, maybe I'll put quotes around it or underline it to know that that's essentially case 1. Now I'm going to move to case 2. Statement 2, f has a limit at x naught, and the limit is f of x naught. We need to prove that f is continuous at x naught. Well, one way of doing it is the delta epsilon proof, because we have to prove that f is continuous at x naught. And the definition of continuity has the delta epsilon definition, so that's what we're going to do. Not that that's the only way to prove it, but we're going to assume that 2 is true to prove this. In order to prove continuity, I need to say let epsilon greater than 0, or let epsilon greater than 0 be given. Since 2 holds, that limit exists, this limit exists, there exists a delta greater than 0, such that x in the domain, and the limit means I need 0 less than, means that x in the domain and x being very close to x naught but not equal to it implies that f of x in absolute values minus f of x naught is less than epsilon. We're almost done, really. The only case that has not been covered is the case when x is equal to x naught. And we can easily say that when x is equal to x naught, f of x minus f of x naught is 0. So it also holds true if I remove this 0 less than. It holds true when x is equal to x naught, and that's really all that we have to prove. So I'll say thus, x in the domain and x minus x naught less than delta implies f of x minus f of x naught less than epsilon. And that's all we had to prove. So the only tough case was, not even the tough case, the only one that was not covered by this limit existing was to prove when x is equal to x naught, that the distance between f of x and f of x naught was less than epsilon. And let me go ahead and say, that's correct. Okay, that's the first two proofs. I ran out of room, so we'll start over in a minute.